Okay. There's that. And let's see. And now to begin. Exponentials and logarithms. Or exponents and logarithms. So I must begin by rewriting each equation in exponential form. So that means saying 11 to the 2 is 121. 9 squared is 81. 7 squared is 49. And 6 to the 1/3 is 216. So you say 11 squared is 121, but you can technically say 11 to the 2 is 121. That's allowed. Here, I could have put down the cube root of whoops. That's actually an error. Just a sec. Yeah, I could have put down the cube root of 216 is 6, but they asked for it in exponential form. That means in the form of a to the power of b. And there are 16 problems to do altogether, so we check the first 4. And they're all correct. Okay. Now write each equation in logarithmic form. Okay, so this can be read aloud mentally as, to what power must I raise 81 in order to get 9? And the answer is 1/2. The answer is 1/2. To what power must I raise the number 81 in order to get 9? And the answer is 1/2. But, you know, mentally I can sort of just swap these two around and then just stick the word log in front. Without any sort of understanding of what's going on. You know, so like here, just mindlessly swapping the 2 and the 256, I obtain this, and that's correct. But again, to what power must I raise 16 in order to get 256? The answer is 2. And you can put brackets around if you want, but they're optional when you have a single argument and there's no potential for ambiguity and getting things mixed up. But you must do brackets when there is potential for that. Okay, and I read it aloud as log base 7 of 49 is 2. Log base 12 of 144 is 2. Like that. And now they render it more abstract, so you can't rely on factual knowledge about perfect powers. The perfect powers are the name for all the square numbers, all the cube numbers, all the fourth powers, all the fifth powers, and so on. Not the first powers, otherwise that would render all natural numbers as perfect powers. So anyhow, you could just sort of, once again, mindlessly swap them, and it'd be totally fine. Like that. But if you're ever in trouble and you want to remember it, the way I do, I use 2, 3, and 8. 2, 3, 8. 2 to the 3 is 8. Log base 2 of 8 is 3. And so it's just a way to mentally remind yourself to just swap those two last two bits of information. That one there and that one there. Yep, okay. So here in exponential form, log base 5 of n is negative 2. Oh, then 5 to the negative 2 is n. Log base 5 of x is 19. Oh, then 5 to the 19 is x. Log base n of m is negative 6. Oh, then that means that n to the negative 6 is m. Okay, and then finally in logarithmic form, but we must check all of these. Okay, the ones above are correct. That's all fine. Okay. Finally, in logarithmic form here. Log base x of 178 is y. Log base 19 of x is negative 19. And we check. And that's correct, and that's good. And now evaluating logarithms. So evaluating, that means actually computing or calculating. So I have knowledge of these perfect powers. The answer is negative 3, because 7 cubed is 343. So this being the reciprocal would be negative 3. The answer is negative 3 again. 2, 3, 2, 2, negative 2. And negative a third. 2, negative 3. 3, negative 3. And we check. And that's all correct. And that's good. And now the inverses of logarithms. 24 problems. Okay. Find the inverse of each function, where y is 2 times log base x of 3. So just going through the procedure whereby we try to isolate the variable x. So first divide both sides by 2. So y over 2 equals log base x of 3. Then raise three to the power of both sides. And then finally swap the variables. And then check to see if it works. But does it work? Well, okay. I mean, if I put 3 in there, then that turns into 1. No, beg your pardon. Yes, it does. It turns into 1, which turns into 2. If I put 3 in there, it doesn't bear any resemblance. All right, so maybe it's not as simple as I thought. I have to think a little bit more. Let's say y is log of x. Well, okay, then 10 to the y is x. And then, so the inverse, swapping the variables, would be this. So we put 1,000 in where x is, and we get out 3. We put a 3 in where x is, and we get out 1,000. Which is what we want. Let's say for this one. Well, if I do x to the power of both sides, I get this, which isn't what I want. But then I have to take the y-th root. So like that. Yeah, that seems fine. All right, we'll try that. So y over 2 is log base x of 3. And then x to the y over 2 is 3. And square both sides. And take the y-th root. And here we go. So y is the x root of 9, like that. And we check by plugging in 9 here. And log base 9 is 3, well, that would be a half. And times that by 2, well, we get 1. And then we plug in 1 there, and the first root of 9 is 9. So that checks out. Okay, here. There's an x up in the power here, so I can move that to the front. And now log base 6 of 3, recall that that's just literally just a number. So you can divide both sides by that. And so the inverse function when you swap the variables, would look like x over log base 6 of 3, I think. But we must check. Okay. So, okay, I don't understand these at all then. Unless I'm getting this totally wrong. Right, okay. That is 3 to the 2. And then the x root is 1 over x. So, yes, that's absolutely fine. That first one. But this one, well, okay, that's strange. So they say log base 3 of 6 to the x. So, so I understand that you could put that in front there like that. But the real way to test this, is with inputs. So I'll input 10 and I'll see what I get. Okay. So log base 6 of 3 to the 10, 6.13. And then I'll put in 6.13 over there. And I'll put in log base 6 of 3. Whereas if I do it over here, no, they're completely equivalent expressions, but I just can't quite see it. Yes, of course I can't see it, because I can't see that when you swap them, that turns it into the reciprocal, doesn't it? Of course it does. Log base 2 of 8 is 3. Log base 8 of 2 is 1/3. So it's clearly a reciprocal. All right, so I'm just not paying attention, am I? But you know what? That's good. It's good that I learned that. Okay, so I need to make x the variable. So, or the isolated variable. So I might do that. And then this. And then 2 to the both sides. Like that. And so, well, y is equal to 2 to the x over 3, I think. And here, 5 to the both sides. Then divide both sides by -2. And then swap the variables. Is it not the case? But I'm pretty sure they're going to say something different to what I say. No, that's actually completely correct. That's fine. Okay. 6 to the both sides. Divide both sides by 3. So then the inverse is this. Take 10 from both sides. You know what? Why don't I swap the variables just at the very start? It's a lot better, right? Okay. Just like that. And then do 4 to the power of both sides. But you know, I like the y to be on the left. And check these. Okay, they're all correct. First move is a swap and moving that 6 over to the left. And next move, 2 to the power of that, and swap the sides. First move, darn it, old habit. And then 6 to the both sides. Check. Okay, good. They would put a bracket around if they meant that, but here this just means log base x of 2 and then take away 6 from it. So just a second. Add 6 to both sides first. Now do x to the power of both sides. And then take this root of both sides. Like that. And then swap the variables. And then here, divide by 4. Log base x of 2. X to the both sides. And take this root of both sides. Which means 1 over this, which means reciprocal. So swapping variables. And we check. And that's correct. And that's good. Okay. Five to the both sides. And then take 5. Like that. both sides over -6. X to the both sides. And then that root of both sides which means the reciprocal. And swap variables. And check. And that's good. Okay, take logs of both sides. And times both sides by 2. And then swap the variables. Take logs of both sides, but log base 4. And times both sides by 3. And swap the variables. So y is equal to 3 log base 4 of x. And check. Okay, so they put the 2 up there, which is fine, because technically they're equivalent. And they also put the 3 up there, which is also fine. But the reason why I put my 2's in the front and my 3 in the front is because multiplication is cheaper than exponentiation, isn't it? Just look up the result in a log table and then double it. Anyway, y take 4 is 3 to the x. So to get x by itself, do log base 3 of both sides. And to get the inverse, swap the variables. And, they might say like log base 3 of x divided by log base 3 of 4 if they want, but that's up to them. But I don't know what on earth is going on with this one. It's its own inverse, self-inverse, as it's the identity function. And check. And that's correct. Okay. Log base 4 of the left. Double the left. Swap the variables. And bring that 2 up here like that. Take 2 from both sides. Do log base 6 of both sides. And then swap the variables. And check. And that's correct. Okay, getting little bit more difficult now. More difficult looking, which is good. So y cubed, and then times both sides by -2, and add 5 to both sides while you're at it. Well, that's equal to a quarter to the power of x. So just do log base a quarter of both sides. There, like that. Square both sides, multiply both sides by -3, and add 9. Like that. And then do log base 5 of both sides. So say that y is equal to log base 5. Like that. And check. Okay, that's all good. Four y to the 4 plus 3. 4y to the 4 plus 3, and then log base 4 of both sides. There, in one step. 4y to the 5 plus 10, natural log of both sides. And that's correct. And that's good. Minus 2y cubed plus 10 log base 6. Okay. Y cubed, 4y cubed, 4y cubed take 8. Log base 5, 4. There. And that's all correct, and that's good. That's good. Okay, be well, be well.